All right. Well, I've gotten the thumbs up, so we're going to go ahead and get started. My name is Matt Jaded, and have at the podium is Christian Jacobson and John Simpson. Christian and I both did our PhD work at the University of Kent in Canterbury, England, and John is just finishing up his final year of his undergraduate, and we thought this was a great opportunity to showcase some of the nice work that he's been doing that feeds so well into our work surrounding concurrency. So the title of our talk has changed many times. We're going to talk about concurrent runtimes and little robots. So here's the roadmap, and you'll see this slide several more times. I'm going to introduce the challenge that we've undertaken, talk a little bit about the project that we're engaged in, give a little bit of history, highlight two particular examples that we think nicely illuminate the use of concurrency in robotics, and then a brief peek into the future, because there's some things that we've started work on as our project has matured, which we think will be particularly relevant and of interest to the Google audience. So number one, this is the challenge. How do we introduce concurrency and parallelism to excited, bright, energetic young students in a way that they'll be well prepared for the massively parallel future that's coming? Actually, I guess given where I'm standing, we're already there. And so this is that there's an educational challenge here. And really what it is it's fundamentally a user-centric problem, okay? We require better tools for the teaching and learning of concurrency. The tools that we've developed in the course of our project, we think they have some intrinsic value outside of the educational context. And what we're going to do is explore a little bit how those tools were applied to our educational problem. And I think that's about it. So that's all we'll have time for. Motivating concurrency. I think there's a big, what do I want to say? I think there's a big stigma attached to concurrency where people think it's hard. And if you listen to educators talk about concurrency and parallelism in teaching computer science, this is too bad, because I think it can be hard, but it does not have to be hard. So what we really want to do is create compelling contexts in which students can learn concurrency. And then we'd also like good solutions to our challenge to be guided by some very sound principles that provide an umbrella for all of our work.
So one of our first principles is that the things we work with need to be authentic. And really, what we mean by that is that often we work with problems that are quite abstract, and they do have a basis in the real world, but still, we often work with them in the abstract, and such as the dining philosopher's problem, which is often set in concurrency courses. And what we are more interested in is really exciting people. So here we have some young women who are actually working with robotics, and we would like to present the problem using these robots as an authentic problem that requires concurrency.
Now, a second principle that we've really used to guide our work is a notion of constructivism. This is a theory of learning that has been around for a long time. And by constructive, what we mean is that when you are engaged in an authentic task, it engenders a kind of learning that generally produces very deep understandings of the material that are very personal. This lecture context is not constructive. But when students like these who are engaged, these pictures are from the first Lego League competition that we've been holding for several years now at the University of Kent. And it's an international competition. You may have heard of it. You can see this young woman is intensely focused on her task. And when students are engaged in this way, when we capture their minds wholly, the kinds of lessons they learn are incredibly powerful. Whether it's a winning success or they feel somehow as they've failed, both of those yield powerful learning experiences.
Okay, so we also believe that solutions should be fun. So at the University of Kent, Matt mentioned that there's the first Lego League competition. And actually, we run this with 20 schools and about 10 students per school. So there's a lot of people come in, and there's a very busy environment, and people work with the robots. And they actually, the students really get engaged with the material. They really enjoy what they're doing, and they get really attached to the kind of things they're working with. If you can move forward. And you can see when when they win, when there are victories, they really feel a sense of belonging to the material they're working with. Can you wind forward again? Personally, I'm here working on the project to do this concurrency work because I encountered it while I was at university, and I thought it was a really interesting and engaging opportunity to work on real research problems outside of the scope of my course. And I've been able to explore things, and I've really thought it's been an enjoyable experience. So that's...
Just to note that the first LEGO League is an effort that requires our entire department. When we say we, we're referring to all of our colleagues, not just the three of us standing here today. So now I'll give you a bit of an overview of the Transterpreter project, the logo for which you see sitting here down in the corner. It's an open source virtual machine. And our kind host, Dave Bort, put together these excellent posters for us. So we've gone ahead and used this symbol that you may have seen and thought was actually a real warning. So the first bit of our project is actually the Transterpreter. It's a bytecode interpreter. It's a very small it's a small virtual machine. It runs on in about 10K. And that lets us interpret a rather interesting bytecode that has built into it some notions of concurrency. What we'll be talking about, as we've said, is educational robotics, and we've worked a lot with the LEGO Mindstorms because it's such an affordable commodity platform. And lastly, as we talk about some of our future directions, we'll talk a bit about 42. That's our experimental compiler for exploring, compiling concurrent and parallel languages. It's the answer to life, the universe, and everything. Written in PLT scheme, and we'll also talk a little bit about some of our explorations of SMP and cluster computing as well. So it's a bit odd to narrate your own video. This is from a presentation that we gave previously where it's hard to do these demos live. So this gives you a chance to see up close what a LEGO Mindstorms looks like. How many of you have seen a LEGO Mindstorms? Okay, actually, almost all of you. So if you'd like, I don't need to dwell on this terribly long 16 megahertz machine, 32K of RAM, 3 sensor inputs, 3 motor outputs. And what we have here is actually a robot that has 2 light sensors. So I'm getting ahead of the video. I don't know if I should. I'll let it run. We have 2 light sensors on this. What's interesting is we have 2 parallel processes connected to them that read from the sensors. And then we have 2 parallel processes that actually talk to the motors. We have a process in between that actually acts as a brain or controller. So when this runs, we have at least 5 or 6 concurrent things going on the Mindstorms, juggled in a very safe and reliable way. So let's go ahead and move on from, see, it follows the line, and it's too late, it's gone. It followed a line.
So one of the goals in actually designing our virtual machine was to explicitly target the LEGO Mindstorms and small platforms like that. And so one, we wanted it to be portable because all of those embedded platforms use a lot of different kinds of processors. We also need it to be small because actually on the LEGO Mindstorms, we don't have very much RAM. We're kind of up with 32 to 16 kilobytes of RAM. And we also want it to be extensible so we can do interesting things with it in the future. And we're really interested in this concurrency aspect, so we have explicit support for concurrency. And that leads into the fact that we're using an explicitly concurrent language, which actually runs on top of this runtime.
So we've been dancing around our virtual machine, the Transterpreter, the language that we compile and run the bytecode from, which is occam-pi. And we've had people come up to us and say, I think it seems like you're excited about what you're doing, but why did you invent a new language? And we didn't. We actually went back and are building on top of a long tradition in terms of concurrency research and languages. In 1968, now Sir Professor Tony Hoare, along with his contemporaries, developed the communicating sequential process algebra. And what this is, it's an algebra for reasoning formally about sequential processes running in parallel. In the 1980s, the Inmos Corporation in the UK developed the Transterpreter, which was a piece of hardware that was designed to be very fast at juggling tens, if not hundreds or more, thousands of concurrent processes. And you could easily network these CPUs together to form a computational mesh, could be a computational mess. That was programmed in the programming language Occam. Occam is a small language, and it is by and large a direct expression of the CSP algebra. So what you have here is a concurrent programming language that is grounded in a formal system that we can actually reason about when talking about concurrency. Now, in the last decade and a half, Peter Welch and others at the University of Kent, as well as colleagues elsewhere, have been extending Occam into the language that they call occam-pi. And what they've done is they've borrowed from the pi calculus and introduced notions of mobility. Excuse me. And so we have notions of both data mobility across disparate or distributed networks. We have notions of channel mobility, process mobility. And today, we have the Transterpreter, which is the project that we built. We wanted to make it so the language could run everywhere. It's 4 years old. It has generated almost 1 PhD. Christian is submitted and is yet to defend. We have 1 more on the way, a number of papers, a few posters, 1 final year project, and we think oodles of other neat stuff. I think it jumps. Oh. So the Transterpreter is a project of many parts. There's a core bytecode interpreter, but as you know, these kind of things languages live in an ecosystem. So there's the various ports that we maintain, which involve a wrapper around the core. We run on the Lego, the cell broadband engine, or the cell processor. It's the core of the PS3, as well as other places. The MSP 430, which is just a very low-power embedded chip produced by Texas Instruments. A linker, a wrapper around the compiler tool chain. A SWIG tool chain that allows us to bind to foreign libraries written in C. And a whole host of applications, native libraries, tests, and so on. The one that I do want to highlight is we actually have a VMware virtual machine that includes all of our tools. And what's nice about it is we can then program simulated robots directly from the VM, so you don't have to go through a large install process. If you have VMware Player installed, you can download our virtual machine and get programming right away against relatively large robotics platforms. And so these are just some videos of some early testing of what are obviously not entirely successful robots. But anyway. I'm the middleman. So what Christian is going to talk to you now is not authentic, it is not constructive, and it is not fun. That is to say, he's going to actually use the producer-consumer problem to illustrate some features of the occam-pi programming language, and then John will talk about an extension of that and how that was used to do some interesting work in robotics, replicating earlier work on the subsumption architecture.
So what we'll be talking about really is, or showing is the occam-pi language, which is what we run on top of the virtual machine. And it has concurrency as a first-class construct. So we're basically able to say, in parallel, run a bunch of things. And it also helps us to ensure safety. So, concurrency isn't an add-on library, it's there in the language. So the compiler and the semantics can actually help us ensure, for example, that we don't have race hazards. And this is in part because processes are entirely self-contained. But if you just look at the kind of normal, a simple producer-consumer scenario, we're just generating some integers, sending them from one to the other. In C or in Java or Python, there's quite a lot of overhead you need to do. You need to spawn some kind of threads processes. You're probably going to have some kind of shared memory solutions. So whenever these things synchronize and exchange data, you need to program some locking in so that they can actually do this successfully. And for a small problem like producer-consumer, that's probably reasonably easy. But as this scales up, it becomes much harder, and you then become likely to introduce various problems related to concurrency, such as the race hazard. And really, you have to focus on low-level concerns as opposed to the kind of higher-level concurrent design issues. And we're really more interested in the higher-level issues. And so if we look at an Occam program, what we often do is we draw things on paper, because actually Occam programming works very well as diagrams. So often we draw an actual producer process. And in this case, we need a consumer process as well. Now, we don't have any shared state, so we need to connect these two things together. And we do that with channels. And so these are point-to-point blocking unbuffered channels. And so they actually both exchange data and synchronize the processes. And you might know these from other message passing systems such as occam-pi. Now, what we then do is once we've designed our system, we can pretty much just turn the crank and turn this diagram into some code. And so what we have is a named process, we call it producer. It actually has a little dot there, which is where we're going to hook up the channel. And so we need a parameter there that actually says we're going to have a channel of integers, and we'll call it out. And so this allows us to hook it up to the other side. And what we then do is we can write some code to actually produce the numbers and send them to the other side. Now, you'll notice perhaps that Occam uses indentation in order to denote scope, much like Python does. But what we have here really is just a process that loops forever, outputs a number, and that's denoted by the bang. And it basically outputs I, and then it increments the number, and we go around again. The consumer is pretty similar. Again, we have a named process. This time it has a channel, which we call in, because we have things coming in. And it just consumes numbers, and it probably would do some kind of work on them. So what we have to do as well, we now have the two simple processes, but they're not yet running in parallel. And so we actually need to put these things up and run them in parallel. And to do that, we just create a container process called main, and then we could just say, in parallel, indented by 2, run these two processes. However, they do need to communicate, and so we do need to make a channel for them to actually communicate across. And so we make a name channel of type integer, and we give that one end to each of the processes. Now, what I've done here is just try to show how the language can help you write safer perhaps concurrent programs. So one thing you might do is use the wrong process in place of some other process you were going to try to use. So here we have a producer-producer network. And obviously, this is probably not really what you want. And because Occam, the compiler is actually able to infer how you communicate on these channels, it can detect that actually you're doing output on both of them. And the compiler can say, no, you cannot compile this because it does not obey the semantics of the occam-pi language. And that's a nice feature, especially for our students who don't have to wrestle with some of the harder problems in concurrency.
So producer-consumer sets us up to see that we have these independent processes that the runtime is responsible for juggling. And it handles underneath the runtime handles the actual transfer of the data and making sure that everything happens safely. What John's going to do is talk a little bit about how he took these ideas, looked at previous research done in robotics, and brought some of that forward into the language. And I won't say more so that he can talk about it instead.
Okay, so when I started using this the concurrency in conjunction with the robotics, I quickly realized that when you're using the concurrency maps well to the inputs and outputs that we have. But it would be good to find a way to build robust and systems we can expand easily. So we looked to Rodney Brooks' subsumption architecture. He wrote a tech report about it in the mid-'80s. And what this does is it takes the complex behavior of a large robotic system and breaks it down into smaller layers of simpler behaviors that can be composed. This field became known as behavioral robotic control and sometimes reactive robotic control. So if we go on with the behavioral control kind of theme, we've got simple layers. They're kind of like, we might think of them like reflexes. If we touch something hot, we'll immediately recall backwards maybe without any cognizant thought about what we're doing. Additionally, we can actually take high-level behaviors and then subsume underlying behaviors with them. This is kind of related to if we wanted to go into a burning house to save a child or something like that, we could actually override our reflex to reach away from the burning door handle and open it anyway. And this is the same kind of idea that when we don't want that basic reaction, we can override it to get more functionality. So this is actually out there in the real world. Rodney Brooks started a company called iRobot. They make the quite popular Roomba vacuum cleaner, robotic vacuum cleaner, and the Scuba sort of floor cleaning thing as well. They've sold over 2 million of these, and these use the behavioural control system. This is very much an emergent from his research. So I sort of took this subsumption architecture and sort of looked at how we could apply it to occam-pi to make reusable robot control systems. So Brooks's system described modules with wires connecting between them. And this is kind of similar to what Christian was showing a few minutes ago. We've got these ideas that there are things that are constantly running, and they're communicating along channels. And so Rodney Brooks was working in these terms. And if you can advance. So we've got these wires wiring between different modules, and all of these modules are running concurrently in the original design of the system. And we can actually keep that true to life in the Occam system. The decomposition into layers is also present. We might take a layer 0 here in this robot that causes it to wander, that causes it to drive into space and randomly pick a heading. But then we might add a layer 1 that picks a defined heading that gets us to a goal where we'd rather be. And that actually overrides the motor commands when it has a better idea of what we'd like to do with the motors. So this is a video of me working in the lab back at Kent. There's quite a lot of stuff in the lab. And actually, this is the Pioneer 3. It's a fully featured Pentium 3 700 computer inside running Debian Linux. And it's actually a really big robot. We have a laser scanner and sonar scanners all around the edges. And actually, this is running the subsumption code that I ended up writing. And so it's using the laser scanner on the front of the robot to explore the space and go forward and turn away from objects it encounters. It also has a safety mechanism built in. If it drives straight into an object, it'll actually stop. So we can start to compose these systems with these occam-pi processes. If we define a behavior that tells us to go forward until we get too close to something and then stop, we can write that fairly easily in terms of process and channels. So we get a channel of laser data in. Maybe we have a process that refines that to get a minimum distance to the nearest object. And then that distance is passed on to a thresholding process that checks it against the kind of distance we'd like to be away from things, and then passes either a stop or go command appropriately. And we can actually look at the occam-pi code for that. At the top of the process, we've got 2 channels defined. We've got a channel of distance in and a channel of motor commands going out. When we come in, we enter a while true loop. We're running concurrently. We can keep doing this over and over again without worrying about the rest of the system. And actually, we can read the minimum distance in, do an if construct over the minimum distance, and then send an appropriate message on to the motors. And so actually, we can start building up some really quite interesting systems by composing these layers. If I wanted an additional behavior that said, well, we want to turn away from objects in front of us because just stopping doesn't really do anything in an enclosed space, I can write some more Occam processes, have some more channels. What's interesting here is that we can have the suppressor, that when we've got output coming from the lower levels, it'll pass straight through in the main case. But actually, when we want to turn away from an object in front of the robot, we can override those go forward messages using the suppressor and actually pass the backup and turn messages to the motor instead. And we haven't modified the behavior of the underlying layer. We've still got the semantics that we would expect from that layer, while we've added more functionality to the robot. And this robot would actually demonstrate a more complex level of behavior. And we can continue to do this arbitrarily. And it's quite interesting to... So I said we had lasers and sonar. So if I added another layer that read from the sonar and checked if there was space behind to back up, because if we head up to a wall and then we try to back up, maybe there's a wall next to it. We'd like to check if there's a wall there, because then maybe we can try and go forward a bit and make a turn with more points. So we can write another process that reads from the sonar, and we introduce a new inhibitor. And we'll see that behavior in a minute, if you can advance. So actually, we activate this layer. We've been backing up, and we don't have space behind to back up into. this layer becomes active, and it activates the inhibitor. What we've done is connect the second layer into the inhibitor, so that actually, when we don't have space behind, we won't actually send those backup and turn messages to the moders. But then the emergent part of this system is that the base layer will then be active, because there's nothing suppressing the go-forward messages. So actually, by adding this extra layer, we're bringing a lower layer back to do some useful work. And all of the layers stay intact as they are. The interactions between those layers are defined in terms of these external processes. And so actually what we get is we get the forward motion without explicitly writing that we wanted forward motion in this new layer that we've added. And so we'll just show that video again, just to sort of know we've related some of the code that's running on the robot. And that's the things it's doing. It lets us build these kind of architected systems that are decomposable into individual pieces that don't change between iterations. And what's nice about this is we actually managed to implement Rodney Brooks's work fairly directly today, even though it was written maybe 20 years ago. And I think that's actually been really interesting to explore.
So it's interesting. So anyway, English language has just left the room. So to reiterate what John said, it's really nice is that Rodney Brooks had this model for how he wanted to do things, and there's something really compelling, I think, about being able to express that model in a way that is directly supported by your underlying language, and you can have tools that can help check the correctness of what you're doing before you turn it into executable code. So what we're going to do is we're just going to give you a peek at some of the things that we're working on as we move into the future. And hopefully those might be sources for questions, or either way, they're just the interesting things that we're working on that we'd like to share. In fact, it's not just that we think they're interesting, it's that we think they're very, very exciting.
So one of the things that we'd really like to do is we have this notion of actually wanting to get across to students that actually concurrency doesn't need to be extremely hard. Now, there has been, back in the heydays of Occam, there's been a number of graphical user interfaces for it. And again, because we have this very graphical notion of the language, and we can actually draw things and almost mechanically turn them into code. And so we'd like to actually be able to give that to our students, because we don't necessarily want them to have to deal with the syntax straight away, because it really, it distracts from some of the objectives related to concurrency that we'd much rather get across. And so what we'd like to do is put this in a program where we can actually build these robotic controllers from components that they can drag off a palette and then put on and wire up, and thus build some robotics controllers. But also, we don't really want to actually hide the power underneath. So we would like to then, once they've got used to the concurrency ideas, to actually then allow them to express them more fully using the full language. And this is really what we're interested in doing, is really start by hiding the complexity and making it available to our students to explore the concurrency concepts, and then unravel things until we actually get down to the syntax and to the code to actually program, and they can actually then start to do some very powerful things.
So in terms of our original educational objectives of authentic, constructive, and fun, what we're really saying is that the tools that you use become a gateway. And they really do shape the way that students think about and encounter and tackle problems. That if we wanted to, our experience from using these Lego robots in the classroom, in my case now since 1998, really there's a lot of inadequate tools for students who are trying to engage in what is a fundamentally concurrent task with a linear control flow based visual language or syntactic language. There's many, Java, C, there's a lot of languages available for these robotic systems, but none of them actually support them in juggling all of the tasks that they need to engage in. And so what we're really trying to do is at some level, provide a powerful way to introduce students to these notions about concurrency and parallelism, so they are more functional as designers of parallel and concurrent code in other languages when they actually have to start implementing it using lower-level primitive constructs. Looking forward, part of what I'm employed right now to do is I'm a postdoctoral researcher at the University of Kent on the DIAS project, which stands for the Design, Implementation, and Adaptation of Wireless Sensor Networks. And what we're doing is it's actually a very ambitious project. It involves 5 institutions, Strathclyde University, Manchester, Glasgow, St. Andrews, and Kent. And we have radio engineers, database experts, language experts, people working on runtimes and hardware, and most importantly, we have scientists. And what we're trying to do is address the kinds of research questions they have in an agile way, bringing together all the different kinds of design that go on in our various disciplines in the development of sensor networks that we can place in the world to study the environment. Now, I don't know if you've thought much about what it takes to actually put sensors in the world and run them for long enough to do interesting research. But usually scientists have questions that they require years' worth of data that's consistent. And really, the state of the art in terms of software development, in terms of power, battery power, and other things, is not prepared to drop a node in a river for 2 years and then come back and have it still be working and have data ready for you. So there's some very difficult challenges. So we've been using the Transterpreter at the runtime level to try and bootstrap us into writing safer concurrent code on these embedded systems, so we don't go out 6 months after deployment and discover that we had a race hazard and got 3 days worth of data. One of our deployment sites is in the Croydon watershed area that's east of Manchester, England. It's a very beautiful area. All these sharp rolling hills where you cannot get a cell phone signal if you try. And so if you deploy your network at the base of these valleys, you really need a way to shuttle data around or alert conditions. So you might then have some kind of mast at the top that can see part, if not all, of your network. And so, to a certain extent, what we're trying to do is use these wireless networks to enable better, longer-lasting research and basically help scientists engage in fundamentally important tasks in asking questions and answering them about the world using these small devices in this way. Another exploration that we've engaged in recently, and actually on our weblog, there's just some initial information, some science numbers and graphs, where we've taken the Transterpreter virtual machine, which when we're running on the Lego is a single threaded fetch and run loop, because the Lego only has one processor. But when we're running on some kind of SMP machine, we have a lot more computational power available. So what we've started working on is we made some very small changes to the interpreter, just a few lines of code, to actually put operating system level threads underneath it. In Occam, as you saw, we have the construct par, and when we put something under it, we'd really love it to actually run in parallel. So what we've seen is that when we thread the interpreter, we can get speed up, even in relatively trivial cases. We've also found that threading models on different operating systems are completely different. And actually, there's a lot more work that we'd have to do before we could claim any kind of general result. There's plenty of research on scheduling algorithms and things for this kind of thing that we've read about, but we wanted to make tiny changes just to do a spike exploration. And what we think is that there's some actual value in pursuing this further. And lastly, on the Darwin H4 cluster, you guys have a few machines available to you. It's probably not as impressive as the cluster I run under my desk. Do people make jokes like that all the time? Yeah, so all right. Got it. We'll chew on foot later. But either way, so what we've done is, I mentioned how we want to be able to make use of, I'll call it legacy C code, although occam-pi is an active and living library. We have this language that has notions of parallelism and channels, and there's a very nice mapping actually between occam-pi channels and occam-pi blocking calls between distributed machines on a network. And so what we'd really like to do, and what I've written some prototype code to do, is that we can First of all, we could model our distributed system in occam-pi. There was a paper published in, oh no, I forgot the IEEE conference, by a gentleman at Skype, where they modeled hundreds of thousands of users on their network using occam-pi. But what would be nice then is if we can then use our, I never corrected that slide. If we could use Occam as some kind of architectural glue, and at key points, break our Occam process network up with open MPI channels, at which point my concurrency and parallelism is still guaranteed to be correct as long as the semantics map correctly from the language to the library. So I think that's something we definitely want to spend more time looking at. And I think that leaves us with just one more exploration that we've been engaged in, and that's 42. It's an experimental compiler written in Scheme. I did my master's work at Indiana University, and I learned from some really great people about languages, and it's an experience that I've always valued as I've moved forward. So what we do is we've taken an even smaller part of the language. Right? Occam-pi is already not large, and implemented a small compiler that we could explore a few key things. Number one, our bytecode interpreter is not hugely fast. It's very portable. And in fact, one of the things that we brought with us today is in a box and it's hidden. We brought a robot that we saw for the first time 2 days ago, a brand new architecture for us. We ported to it, and we actually now have John's subsumption code running on top of it. You're welcome to come up and take a look at a real robot running around on the floor after the talk. But what we'd really like when we're dealing with, oh, thanks, Dave. So there it is. It's a, it's a little robot. There. So we'll run him around on the floor in a little bit. But what we've started to explore with the compiler is native code generation. We're actually able to use the existing code base as runtime support for compiled code. So instead of doing bytecode interpretation, we can sort of unroll things and get some initially very impressive numbers, executing at near native C speeds, while maintaining, again, our goal of safe concurrency on a platform. Our colleague Damien Dimich is looking at code distribution. He's been playing with the cell broadband engine, and we're interested in whether or not we can, at compile time or dynamically at runtime, do distribution of processes over a changing set of resources in a distributed context. But that's an interesting and challenging linguistic challenge. And lastly, it's also been a place for us to explore compiler design. I've been playing around with some interesting ideas with units and mixins for composing many passes in a compiler. But either way, so just another spike, which brings us to the end of our talk. And there's a lot of people who have been part of it or helped out in a number of ways.
Yeah, so there's quite a few people we need to talk. My supervisor, Peter Welsh, and also David Wood and Fred Barnes, who've been instrumental in updating Occam to occam-pi.
Our colleagues, Damien Dimich, who's recently started his PhD at Kent, Carl Ritson, who's just finished his third year at Kent and is now doing a postdoc project. Carl did some very nice things exploring, helping support some of the multi-threading, as did Adam, who's finishing up his PhD not too long from now. The University of Kent has been very supportive, and in particular, we have to give thanks to Jenny Oatley. Jenny is actually the secretary to the director, but I don't know what your experiences in life have been, but she helps make things happen. Of course, the EPSRC for funding me as a postdoc and for supporting some of this work. And we also want to thank Dave Bort, who's been our host here at Google. So that's about it. We don't have a slide with our URL on it, which is unfortunate because the word Transterpreter is actually rather hard to spell. But that's the end of our talk. And thank you for taking some time to listen to us. So if there are questions, I think I'll just go ahead and I can point at people if you have any questions. Yes, sir.
So is the focus of the end results you guys are looking for mostly in real-time systems, embedded systems, small systems, or massively parallel infrastructure?
It's
Or both?
Okay, so yes, repeat the question. So the question was, is our primary focus embedded systems, these small systems, or is it that we're more interested perhaps in the massively parallel and distributed? Our initial goal was to get Occam running everywhere, which I think we've done a nice job of demonstrating. We haven't yet encountered something we can't run on. And it was originally a language for running on small platforms and embedded systems. What's interesting is that because of the approach of using an interpreter, making it easy to bind to other languages, we've been engaged in these spike explorations. I'm not 100% the language as it sits would necessarily be completely appropriate for anything and everything in the distributed paradigm, but certainly there's something compelling about it as being an architectural glue language, where perhaps I have my high-performance libraries written in C for doing numerical crunching or data processing. But at a higher level, I use a language that my compiler can help check me afterwards to say, yes, when you go and you run this job on your 100, 1,000 unit cluster, you're not going to run into something that you hadn't anticipated. Although we're 4 years old, I guess another way to put it is we're just reaching the point now where we can do these interesting explorations. Does that make sense? Any other questions? We've stunned them with our very, very exciting. Oh, the robot, yes. Go ahead, Christian. You've been hacking on it most recently.
So I think while we would like it to run around, I think we've had a bad flash experience here, flashing.
Oh, no.
So unfortunately, I managed to destroy the program. Sorry. Yeah. The problem is that we flashed it over
Zigbee,
the
Zigbee.
11, and so there's a lot of interference with all the wireless here. So it doesn't really go so well. So all we need is a lift or something like that, like a Faraday cage, and then we can get the program back.
But it's true. We were at AAAI Robotics at Stanford earlier, just the last few days, and whenever we wanted to flash this thing, because Stanford also has a fair bit of wireless networking, we'd either climb into the basement of a stairwell or an elevator, and funny, the upload worked. But you know, somebody decided RS-232 is no longer viable, so our machines don't have it. We'll try and fix that and show it to you before long. Any other questions? All right. Well, thank you all for your time.
Thank you.